Hello, everyone. Thanks for joining us for our next live session. I'll be your producer for our session, but before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer. Our session is being recorded. It will be available to view on demand right here on the Microsoft Reactor channel. With that, I'll turn it over to our speaker for today. Thanks for joining us.
Hi, everybody, and yeah, great to have you here. My name is Anthony Shaw. I work for Microsoft. I'm the Python advocacy lead at Microsoft. I'm also an AI researcher. I'm a fellow at McCullough University in Sydney as well, and I do some AI research there. Stephen, do you want to introduce yourself?
Sure thing. Hey, everyone. My name is Stephen McCulla, and I am an AI solutions architect with NVIDIA. So that means that I get to work with Microsoft on all these cool things around AI and involving Azure and NVIDIA together. And a bit more on that. So Microsoft and NVIDIA have been in close partnership to power the next generation of AI through the deep integration between NVIDIA's accelerated computing platforms with Microsoft's global cloud infrastructure via Azure. And this webinar series is a big part of that partnership. We want to work together to show users like you how to best leverage the magic that happens between Azure and NVIDIA together. So make sure to tune in to this episode and the rest of the series as we explore these integrations and show you how to best apply them in the real world.
Great, thanks, Stephen. So today we've jumped forward to the agenda. Okay, so this is a pretty deep technical session. We're going to be getting into some details around AI inference and the performance of AI models. But before we do that, I'm going to cover off what exactly that means and what is AI performance and what factors are there involved. Talk about sort of usability of AI and what role performance has in kind of user experiences and adding AI into features. And Stephen's going to kind of take you under the hood, and we're going to look at the nuts and bolts of what's actually happening when you're communicating with an AI or using it to generate something. We'll talk about benchmarking and then like what things you can actually take home and use today to accelerate performance, some tricks that we know, and then we'll kind of finish up with what's on the absolute bleeding edge of techniques that we can apply in AI today. Okay, so when we talk about performance, normally when we talk about application performance or server performance, we think about speed. When we talk about performance in AI, it's a little bit different because it's quite a broad term that can mean lots of different things. We could be talking about the model performance, which is the word we use is accuracy. What that actually looks like is how well a model can correctly analyze something, identify something, answer a question, how well it can extract information, or how relevant the response is. There's kind of lots of fairly subjective measures for accuracy. So we've basically built up hundreds of different benchmarks, and you can see lots of interesting leaderboards online as to which is the best model for a particular task. We then also have regression metrics so that we can look at when you go from one version of a model to another, how does that impact the performance of its accuracy against those existing benchmarks? And then also, does that particular model have a bias, or what is the safety sort of controls around that particular model? So there's a lot involved in picking a particular model and looking at the performance of that model when it comes to those kind of metrics. We also look at, and the thing we'll be talking pretty much exclusively about today is the actual serving performance. And there's kind of two metrics that we use for serving performance. One is latency, and the other one is throughput. And they're both equally important because they impact how long it takes for the AI to respond to the application or to the user. And there's different reasons behind both of those two, and there are different kind of techniques and tools that you use to improve the performance of either of them. Next slide. Cool. And the measurements you would use depend on the use case. When we have different types of AI models, the one that is probably most talked about right now is large language models, but there are lots of other types of models as well. There's models for videos, there's model for audio. Those we call modalities. So, what information are you putting in? So if you put in video and you ask the AI to identify objects, for example, that's like a video to text model. We also have embedding models, which are used in RAG, re-ranking, which is used in relevance and search, and as well as world generation, which is used in more sort of complicated scenarios. So the measurements, these are different types of models. However, the nuts and bolts of how the actual inference works and how the AI runs is generally being standardized over time. So a lot of the actual inferencing engines can do video models, they can do audio models, and they can do text generation models as well. So the actual runtime itself, the sort of tuning, I guess you would do of the engine depends largely on which models you're running, and the hardware requirements definitely depend on what kind of model you'd want to run. So, if you wanted to do a video model, for example, those are probably the ones with the highest requirements in terms of hardware, whereas text generation is sort of not too bad. Embedding models are the things that you can run definitely on your mobile phone. We've got plenty of embedding models running on mobile devices. So the actual applications then is what sits on top of that. So, are we looking at a interactive text kind of AI? Is it something to do with images or videos? Coding agents are really interesting nowadays and a great use case of this. And increasingly, we've got agentic as well, where we're getting the AI to kind of communicate with tools and giving it the ability to go out and take actions and not just produce text or images. Next slide. Cool. So when we're planning for performance, I think it's important to keep in context what the user is expecting. And I've kind of got three levels in this graph. And this is based on lots of testing of over the last couple of decades of local environments. So like trying to optimize applications on desktop environments and servers, and also trying to optimize network applications. So things online, web apps, for example. In terms of what the users expect, it differs depending on what the context is. So if you pick up your phone and you launch an app on your phone, you'd expect it to respond instantly. If you're swiping around on a device or clicking on things on your desktop, you expect that to respond instantly. And so you've got this instinct that things should respond within 10 milliseconds to 100 milliseconds. If they don't, you'd call the application laggy, and you'd assume that there's something wrong with either the app or the hardware. If you're looking at something online, so you're starting to stream a video on Netflix, or you're clicking on something on a website, your expectations are different because you know that potentially what you're communicating with is further away. So normally when I'm in Australia and I'm loading something which is in Sweden, we've got a lot of resources in Sweden right now. I know that there's 300, 500 milliseconds between me and Sweden. So the fact that it could take a second to load is fine. And I have that expectation as a user. AI is even further to the right, because today, a lot of AI applications, definitely, and the AI itself can take several seconds to finish, if not longer. So when the users are interacting with chat applications now and they know that it's AI based, there is a certain level of patience that they have to communicate with it and wait for it to respond. What we're really trying to do is to minimize that, and also think about that context when you put AI into applications. Next slide. So really kind of what you're trying to do is align your user experience and your expectations. So if you had a keyword-based search on your app, then the user types in the name of a particular product that they want to find on the website, and they click search, their expectation is it will find that more or less instantly. If you build that out, if you decided to just introduce an LLM to every single search query where users were used to doing keyword search, then you've taken something which was previously 100 milliseconds and now made it a second, if not longer. And the challenge is that if the user is used to just typing in the name of a product So like I know exactly what I'm looking for, the model, and I type that in at the top. I don't necessarily need an LLM to spice up my search query, especially if it takes an extra second for it to do that. So the reason I bring this up is because it's kind of tempting to add AI into these experiences, but you need to keep into account the context of what the user is expecting with the time it takes to complete something. Sometimes this is actually fine because if you have a deep research question or the users ask the AI to go and do something which would otherwise take them, hours, weeks, or if not longer, it's completely fine for it to take several hours and to come back and notify you. A good example is deep research, where you give it a research question. It could go and study, tens of papers. It can go and look at hundreds of websites and then come back to you with a complex report of what it's found. In that context, I think it's perfectly fine for that to take several hours, because the user's like, well, that would take me a lot longer, and actually I'm automating something and saving time. So I think it's important when you kind of think about where you kind of put AI into your application to think about the context of it. Is this something that can happen asynchronously? And if not, how long will it take? And can I try and minimize the time? So the kind of do's and don'ts we have, there's a link in the top right, which is to Hacks, which is the human AI experiences, which is a kind of our usability guidelines for building AI into your applications. And there's kind of three don't points that I pulled out of this, particularly about performance. That if you put AI in the way of something which is otherwise a really fast and efficient task without a very good reason, then you're going to kind of frustrate users because they're expecting something to respond instantly or within 100 milliseconds, let's say. If that now takes several seconds to finish, people will get frustrated. The other thing is that you shouldn't necessarily wait for the AI to finish its entire result. We call this streaming, and Stephen will talk about kind of actually what happens when it starts to produce tokens and send information back. But from a usability side, though, when I interact with something, as it starts to send information back to me or starts to communicate back, it gives me this loading idea, or I can read it as it goes. And that's a better user experience than just sitting there getting absolutely nothing for 10 seconds and then just seeing like a huge paragraph of text. My other point is that it's really tempting to use reasoning models at the moment because they score really well on math tests, on other benchmarks and stuff like that, but they're very specific to that use case. And where you might otherwise have used a chat model previously, I wouldn't suggest using a reasoning model, especially for chat applications, unless you specifically need it to, because the performance of these models is designed to solve complex tasks, and therefore they take a lot longer and they use more tokens. You definitely should, though, try and look at where you can use AI to enrich features. But in some circumstances, you kind of want to have the option for users to kind of make that choice, or to dismiss or disable some of those functionality. The other thing we have in the hacks guidelines is that you should say that something is AI generated when you produce the output, and also giving the users the ability to provide feedback. So if it produces something they don't like, you can kind of give a thumbs up or leave a comment. That's part of the guidelines and something we build into all our products. And then if you know that it is going to take a while, it should therefore be asynchronous, and you have the option to notify the user later. And these are kind of things you should build into your design as you're looking at AI in your apps. Next slide. Cool.
So yeah, thank you, Anthony, for setting up, sort of the importance of performance across different use cases. That's a great thing to keep in mind as you go throughout this presentation. Now, before we start talking about how we can improve performance, we need to have a foundational understanding of how these LLMs are working, how they are predicting the next token, how they are generating context, and how they are establishing sort of their chain of thought. So really, this comes down to how the LLM predicts the next token in a sequence. Really, all LLMs are doing is predicting the next best token given the initial prompt. So if I give an LLM a prompt that says, make me sound smart, it's going to think about that. And it's going to, crunch all the numbers, do a ton of calculations, and say that the best next token is the word LLM. And there's a lot of really intense computation going on here. So that's what we're going to jump into. So whenever I say, make me sound smart, the model encodes this information and passes it through its model weights, through its neural network, and it establishes a key matrix and a value matrix. Now, we won't go too much into depth on those, but essentially they keep track of the positional embeddings and of the attention for each of the tokens provided in the prompt. So establishing these values is very, very important, and it's also very computationally expensive. This diagram might look simple, but really there is just an absolute, metric ton of computation going on here to establish the key and value matrices. So whenever the LLM is creating the next token, which in this case is the word LLM, it of course has to look at every single token that has come before it and create the key and value vectors for each of those tokens. And that's just to create a single next token. So we have to do this for every single token that comes after our prompt. So, the first one is LLM, and then maybe the next word is training. So if we finally found, LLM is the best next token, then the next best token, we have to think about it. We recalculate the K and V matrices, and then the next best token is training. So it has to go through that entire process again of generating those embeddings, creating those key and value vectors, and building up these key and value matrices again. So an important thing to note here is that these key and value vectors for the tokens don't change. So for example, the key and value vector for the word make isn't going to change no matter how far we get down that generation process. If our LLM generates 100 tokens from here, the word make is still going to have the same key and value matrix vectors. So you might think to yourself, well, if we're going to be using the same values or generating the same key and value vectors, why don't we just store them and reuse them for every token that we generate? And that's exactly what pretty much every LLM is doing nowadays. It's called the KV cache. So with the KV cache, you are essentially storing the key for K and the V for value matrices in your GPU memory, and you're reloading those with every new token that is generated. Because like I mentioned, you can either regenerate for every new token, you're going to have to regenerate the embeddings and vectors for the word make, or you could just generate those vectors once and then store it in a cache. And for every new token, you just read from that cache. So that cache, of course, is the KV cache. And this is a core fundamental function of how LLMs generate tokens. This KV cache is a huge part of LLM inference, and there is lots of work going into optimizing how the KV cache works and making it faster overall. So whenever we are talking about inference and performance, there are two major stages of this that we are talking about. Really, there's only two major stages in the inference cycle at all. The first is prefill, and the prefill phase is essentially taking the entire prompt and processing it and creating those key and value matrices. That's the entire prefill process. You haven't gotten to the generation or token generation part yet. Prefill is just the model essentially thinking about this prompt, building up these key and value matrices and storing them in a cache. And so when it starts to generate tokens, it has all of that value already. And if you ever submit a prompt to an LLM and maybe it takes a half a second or a second or 2 seconds to just get back even that first token before you see anything coming back, that half second or 2 seconds that the model is waiting, this prefill process is exactly what's happening. This LLM is taking your prompt that you gave it. It is creating this KV cache and essentially preparing itself to start generating tokens. So this is what we call latency. It's the time it takes for a model to just return the first output token. So you might also hear it called time to first token or latency, but really it just refers to how long it takes for the model to just return a single output token. And if you hear the word latency or time to first token, I want you to think of the prefill process. That is exactly what is going on under the hood that is causing latency. Now, once the KV cache is built up from the prompt and we are ready to start generating tokens, then we move into the decode phase. And in this phase, the LLM is generating each token sequentially. And with every token it generates, it adds the key and value vectors for that new generated token back into that KV cache. So every future token after that generated one can still reference that K and V value. So whenever your model starts generating, one token after another, and it's streaming back and it looks really nice, just your entire, 8th grade homework essay coming out of the LLM, that is the decode process. And if you notice it going really slow or really fast, that's the throughput that we're talking about. We measure throughput in tokens per second. This is how much the model is, or how quickly the model is generating new tokens. And whenever you think of tokens per second or throughput, think of the decode process. So another very important thing that we need to consider whenever we are measuring and improving LLM performance. So those are the two major phases of LLM inference, is prefill and decode. But we also need to understand that the LLM isn't just processing a single prompt at a time. Really, your LLM is processing multiple prompts at any given moment using something called batching. And batching is a fantastic technique because it increases the utilization of your GPUs significantly. If you just have one prompt being processed after the other in sequence, you're probably not going to get the maximum utilization out of your GPUs. You might have the fastest latency and the fastest throughput if you're just doing that, but the fastest latency, but you're not going to have the highest throughput you can get, and you're not going to have, you're not going to be able to serve multiple requests at once. So batching is really important here. It's used in pretty much every LLM inference platform. And it's something that is important because it's a fantastic technique to increase your throughput. So as we're talking about, latency and throughput and how we can measure those, it's important to talk about the tools that we use to do that. And that's done, of course, by the almighty benchmark. So when we talk about benchmarks, like Anthony mentioned earlier, there are benchmarks that focus on the model itself, right? They focus on, solving SATs, or they focus on solving, Olympiad math problems, IMO, International Math Olympiad, or they focus on, humanities last exam as another famous benchmark to test models' intelligence. But these are all meant to test essentially the intelligence of a model. But what we're looking at today is the throughput and latency and the performance of the model. So when we're doing that, there are a couple different areas we need to look at. The first, starting at a lower level, closer to the model itself, is the LLM engine. So we can use TRT LLM or TensorRT LLM. And we can use its benching functionality to really get an in-depth view of what exactly our LLM is doing and how well it is performing in very high detail. So TRT LLM Bench, it's open source. It's a fantastic tool to use to really just see what is going on inside your LLM. If we move a bit up the stack, we can start measuring an LLM endpoint. So if you have, served a model yourself using, VLLM or TRT LLM or SGLang, usually when you start running the model, these inference engines will create an API endpoint that you can use to send your prompts directly to the model. So it makes it very, very convenient. And really, this is pretty much how every model is served, right? You have the model itself, then you have the inference engine, which runs the model and creates that API endpoint. So we can measure that endpoint directly by using a couple different tools. NVIDIA has a tool called GenAI Perf, which is fantastic. There's also SGLang bench serving, which is great. There's lots of tools out there to measure performance of LLM endpoints. And the really nice thing about these tools is that they're so flexible, because you can point these tools to measure an endpoint that's running locally. You can measure it, or you can point them to, let's say, a hosted model on, Anthropic or OpenAI's platform, or you can point them to your own model running on Azure. So there's lots of ways you can use these tools, and pretty much you can measure any LLM endpoint that's available to you. Now, a bit further up the stack, whenever we are using LLMs in our application, we also need to have a good idea of the big picture as far as application performance with this LLM. And that's where Azure Load Testing comes in. Azure Load Testing is fantastic for really benchmarking and testing your application across lots of different workloads and benchmarks. So Anthony will show us that in a second. But this is a great tool to get that big picture, holistic view of your application's performance. Now, when you are benchmarking a model, what is going on in the background is that your benchmarking tool is sending a ton of requests to the model and measuring the latency and the throughput that it's seeing from those requests. So these prompts that the tool is using is very, very important, because if you are using prompts that are kind of all over the place and don't really represent your actual production like use cases and the prompts and data that you see in production, your benchmarks might not be an accurate representation of what you're going to see with your model in production. The ideal use case for your data sets, or the ideal setup for your data sets, is to have data that really accurately mimics the data that you have in production, the data that your LLM is actually going to see. So a couple things that really affect that is the data type, or the modality, so whether it's text or code or images or video, as well as the size of the prompts and the size of the context given to the LLM, otherwise called input sequence lengths. A couple other things here to keep in mind when you are creating your data sets for benchmarks, but this is something very important that really helps you nail down performance as you're going through your ML ops or DevOps pipeline. So I wanted to show you in real time what it looks like to actually run a benchmark. So this is a Azure standard NC24 virtual machine. So it's running a single NVIDIA H100 GPU on it. And right now I'm running the Mistral 7B v0.1 instruct model locally on this VM. And so I'll just ask it, or I'll just submit a quick health check to make sure everything's running. So asking it to tell a joke about the sun and the moon. Why did the sun and the moon go to a party together? Because they were celestial buddies. Why did the sun marry the moon? Because he was totally eclipsed by her. That's actually a really good one. And so, I mean, one thing to notice here is just how quick it's creating these answers, right? This is, all the way from here to here, which is maybe roughly 50 tokens or so, and it's doing that in less than a second. So it is very, very high throughput and very low latency that we can see on Azure's infrastructure. Okay, so now we know it's up and running. Now we can run a benchmark using NVIDIA's GenAI Perf tool. So this is the command that we're using. Pretty simple. We're pointing it to our endpoint. We're saying the input token, or the input sequence length, will be 3,200 tokens long. So that's going to be essentially the size of the prompts that we're using. They're going to be synthetically generated, but you could bring your own data set if you want to. And then we're ready to go. So if I run this script, it will pick up this tool, and you'll see here that what it's doing is it's submitting 8 concurrent requests and a total of 40. So it's going to end up at about 5 batches with 40 requests total. And you can see that it returned the request latency. Keep in mind, this is the round trip, like end-to-end latency. So this isn't the first token latency that we're seeing right here. This is how long it took to submit or to complete the entire request. And then our output token throughput is 913 tokens per second, which is, of course, blazingly fast, creating almost 1,000 tokens per second off of just one GPU. So the throughput that we can see that's available to you on Azure is very, very high, and you can serve lots of customers, lots of concurrent requests just off of a single GPU, which is fantastic. So I'll hand it to Anthony to talk a bit more about using Azure Load Testing to get a holistic view of your application's performance.
Thanks, Stephen. If we just switch to my screen. Thanks. So, yeah, Stephen's kind of showing a sort of fairly low-level benchmarking tools where you're kind of running it practically on the metal or as close to that as you can. And those kind of benchmarking tools are great, so you know what the potential throughput is for a server or for an environment. And then you can look at also and compare different models. So that's like a really nice technique. The other implication is that when you actually put it into an application, you want to see how long will it actually take for users to interact with it, to ask it questions. And so what I've done is I've put together a load test. This is using a framework called Locust. This is a free and open source framework. You can actually run this unit test, this load test, sorry. You can run this locally. It doesn't need to be hosted on Azure, but I'm going to show you this hosted on Azure because this is a kind of interesting scenario. So what I've done with this test is I've created a chat user, and they're going to interact with our chat application, which is a web app. And we have behind that an LLM, and that LLM has been given a set of instructions about what it can and can't do. And it's also connected to some tools, so it can like look up orders for users and stuff like that. So when you're putting these load tests together, generally you want to sort of vary the questions that you ask it. So I've put together like a range of different questions that it would start the conversation with, and then the AI would then respond and potentially also look up some of that information in the backend using the tools. And then what we've done in the actual web app is I've deployed this Locust test to Azure Load Testing, and I've run this over a period of 24 hours. The reason I've done that is because I want to get a really good measure for, I think I did it for, this is for 5 users. So 5 users are basically every few seconds or every half a minute, they'd start another conversation with the app. And then it would measure how long it took the app to fully respond to the user with an answer. And so that rounded up to about 34,000 requests over a day. So that also gives me an idea of like, if we have a range of users and they're all using this feature, like how fast or slow will it be? So I'm interested in this because I wanted to understand, how does that go up over the day? And then I can actually dig into some of those metrics. And because our application's got open telemetry in there, so open telemetry is an open standard for basically tracing and metrics for any application, whether it's built in Java, Python, JavaScript, C#, it doesn't really matter. Anything can be traced using open telemetry. So whilst I'm running the load test, I'm also capturing all of this trace information about what's actually happening in the app. And that's useful for me because I can jump into App Insights, and then whilst this load test is running, I've got not just the response times, but I've also got like the averages and how they work out. So what I see is this distribution graph, which kind of shows me the expected time. So like, here's the distribution in time. So going from, very, very fast all the way to concerningly slow, several minutes in some cases. So something must have gone very wrong there. But I can see like most users would be in this sort of 5 to 10, 15 second mark. So what I can do is I can jump in the middle of that, and then maybe drill into one of those particular samples and look at, if I go back, let's drill into the slower ones because I always find those interesting as an engineer. So if I drill into one of those samples, the one that took 13 seconds as an example, then I've got a view in here as to what happened when that conversation went through. So we've got an agent which ran. We had a chat conversation. They asked, "Has my order been processed yet?" And it went through and collected some orders, and then it went through a second time. Now, what's really important here is that the user didn't specify which order, and I have a tool that I've connected to my app called Get Orders, and it doesn't have any parameters to say how like what order, how many, what information do you want. It just gives you back a bunch of different data from the database that actually wasn't necessarily related to the question. And the reason that's important is because that initial request to the LLM actually only took a couple of seconds, but the second request is the one that's taking the longest time. And this second request is where the AI then has to figure out, okay, here's all some information from a database, here's some context for the user, and it's actually spending a lot longer thinking about the answer and sending it back. Now, the reason the load test is important is because, in this case, the LLM itself is pretty fast, but the mistake is actually in the application design because we've plugged tools into the agent in this case. What we've made the mistake of doing is not being specific enough in the initial prompt to say what capabilities this agent has. So the agent's trying its best to try and answer the question, but whilst it's thinking about that and doing it and talking back to the user and capturing information from tools, it is wasting tokens and it's wasting time. And so the load test has been a really useful tool here because it's helped me identify, as kind of the person managing this agent, okay, why is it taking so long to respond? And actually the answer in this case was that we need to really to optimize our prompt. And that's one of the things we can identify here. And we'll kind of come back to that technique a bit later, which is about how prompts are related to performance in general. So if we go back to the other screen. Great. So yeah, my point here is that you can ask a simple question to an LLM. It can take a lot of time to respond. So in this case, we've actually compared two different models. One is a chat model and one is a reasoning model. And that's one of the points I made earlier in this talk was that you shouldn't use reasoning models unless you really need to. And the reason is because on the right-hand side, the reasoning model took over a minute to respond, and the chat model took a second to respond to the same question. The question itself is a general knowledge. Well, maybe not quite general knowledge. Not everybody knows the capital of Azerbaijan, but it falls into the category of general knowledge. And the reasoning model is then going to think about why are you asking this question? It's going to talk to itself for a minute, and then it's going to give you in this case, it gave me several paragraphs about Baku and its cultural history, whereas the chat model will just give you the answer. And this is important because a longer answer equals a longer time because we measure the throughput in tokens per second. So if the question that you ask the LLM is going to produce a long answer, that is consequentially going to take a longer time because the LLM has to produce more tokens. So what you need to do when you're thinking about your prompts is the application, is this LLM use case, is this to produce long answers to long responses? Am I, writing essays? If so, be specific in your prompt. If you need short, concise answers and it needs to be fast, then you need to be specific on your prompt to say that's what you're expecting the LLM to do. So I want it to be short and concise. I only want 2 sentences. I only want 2 bullet points. You need to kind of tell it in the prompt what your expectations are about the output, because that will reduce the cost significantly, and it will also reduce the time it takes to respond. Next slide. Cool. The other technique we have is the actual values themselves. So kind of Stephen was talking earlier about how you've got these different layers in the model, and both in the prefill stage and in the actual token generation stage. Basically, what we're doing in the processor is we're making lots and lots of multiplications of these matrices. And in terms of the actual processor itself, these multiplications are of floating point numbers. And the standard that's been around for a long time, 50 years, probably more, is that you have a 16-bit or a 32-bit floating point number. And processors are kind of been optimized to multiply those numbers. What we found kind of over time is that since we have 64-bit computers or we have 128-bit registers, for example, you can actually get a single instruction which can make multiple operations at once. So whereas you can normally only do one multiplication at a time on a CPU or on a GPU core, if you actually stuff multiple values into that register, you can do multiple instructions at once. This technique's been around for a while, but it's basically been hypercharged by AI. And that's one of the techniques that we use is to try and fit a model into a smaller precision format. So basically try and get it to use fewer bits even. so that you can do more calculations at once. So if you reduce the size from 16 bits to 4 bits, you almost effectively improve the performance by 4x. The downside of that is that by going down in the precision scale to smaller numbers, you kind of lose a bit of accuracy in the model. And that's the thing we talked about at the beginning. We kind of talk about model accuracy. The actual consequence of that is that it performs slightly worse in benchmarks across the board. So tool calling benchmarks, in math benchmarks, in relevance benchmarks, it will perform slightly worse as you go down at smaller and smaller precision values. But in some cases, that's actually acceptable. So, or we have techniques where we can kind of optimize it. So even with a 8-bit or a 4-bit value, we can get very impressive performance out of the model. The reason you'd want to consider these quantized models is because, firstly, we can improve the throughput, 2, 4, 8x potentially. And the second reason is because the amount of memory you need to load the model and actually process the data is a lot smaller. So basically, we're kind of compressing the model. The other analogy I use for this is that if you have like a super high megapixel camera, like a 30 megapixel camera on the iPhone these days, and you take a picture and you compress that down into a smaller image, using JPEG compression, you can still recognize what everything is, but you don't get the level of detail. And that's kind of what ends up happening with these quantized models, is that you can compress them down, 2, 4, 8x even. But each time you're kind of losing a bit of precision and you're losing a bit of accuracy as well. Cool. Over to you, Steven.
Yeah. The precision is a major factor in kind of the performance you can get and also the size of your model, which is great because if you can reduce the size of your model, you can save, you don't need as much GPU memory, and you can save a lot of costs there. So it's great for cost savings as well. And speaking of GPUs and hardware, that is obviously a major factor in the performance that you get from your model. With every generation that comes out, from Ampere to Hopper to now Blackwell, we see massive gains in inference performance. And, we expect that to continue far into the future with every proceeding generation. Obviously, if you're running on just a CPU, your throughput and your latency is going to be, pretty abysmal. And because the hardware is simply just not meant to run LLMs. But if you're using something like, NVIDIA's chips that are really geared for this kind of stuff, that's where you see massive performance boosts. So the hardware that you're running on is probably one of, if not the most significant choice you could make for your LLM performance. Now, Anthony touched on this a bit earlier about the sequence lengths. So when talking about the prompt engineering, the size of your prompt has a lot to do with the performance that you get, specifically on the latency side, because during that prefill process, your entire prompt has to be built and embedded into the KV cache. And if you have a prompt that is 100,000 tokens, that's going to take a fairly long time to complete that prefill process. So the smaller your prompt, the lower your input sequence length, the better. But of course, as long as you're not losing too much on the quality of your outputs. So this graph shows a bit about the correlation between input sequence length and latency. So we can see that generally when input sequence length increases, we see an increase in latency. But unfortunately, this doesn't extrapolate to much larger input sequence lengths, where you would see significant increases in latency once you hit a certain threshold. But yeah, generally, larger input sequence lengths lead to higher latency. Now, I touched on batching earlier and how it works. And batching is great to increase your throughput to a certain point. You can see that this graph, which covers the size of your batch versus your throughput, kind of tapers off after you get to a certain batch size. And that's because no matter how many prompts you're trying to process at any given moment, your hardware can only handle so much. So if you create a batch size of 3,000, it's probably not going to be much better because your GPU is already saturated. But if you find the right batch size where it makes sense, you can see significant increases in throughput and concurrency, and you may have an increase in latency, but that's really up to you to figure out what that sweet spot is for latency and throughput. And batching is a great tool to kind of find that sweet spot. So when it comes to the infrastructure that you're actually using to run your models, it's really hard to beat Azure and all of the services that come around this ecosystem. So whether you're running your models on AKS or Azure Container Apps or Azure ML or AI Foundry, there's really this entire ecosystem is optimized for AI ML. And it's a fantastic way to get your hands dirty and start running your own models with the pay-as-you-go model. So whenever you're using AI Foundry in particular, I encourage you to go and check out the NVIDIA Nemotron models. We have 3 models on there currently, with more on the way. And these models are pretty exquisite. They are entirely open source, everything down from the models to the data sets to the libraries and the research papers around those models. It's all publicly available. So it's a great way for you to become very familiar with these, really in-depth AI topics. And not to mention, the performance that you see from these models is very, very high performance especially for the size of the model. What we've seen with Nemotron Nano in particular is that we see 6x higher throughput with the Nemotron Nano than the throughput of similarly sized models. So it's a fantastic sort of model family, and I encourage you to check it out on AI Foundry. So, we talked a bit about, how we can improve performance, but there are some special techniques that have been, taking shape over the past couple of years that are really take your performance to the next level. So one of these, which is, one of my favorite things to dive into, is called speculative decoding, or SpecDec for short. Essentially, what you're doing with SpecDec is, instead of running one model, you're actually running 2 models at the same time. You're running your target model, which is, a larger model, think, GPT OSS or Llama or Nemotron. And that's your larger, slower, more intelligent target model. But at the same time with SpecDec, you are running a draft model, which is a smaller, less intelligent, but much faster model. And these are usually between 1 to 10 billion parameters. So they're very small, and they can they can run inference very, very quickly. And the way it works is the draft model will begin creating or generating tokens before the target model has a chance to start generating. So what we see is the draft model will, so let's say, the input is V quick. Then the draft model says brown fox hopped over, and it generates these tokens quickly, but maybe it's not the most accurate. And then by the time the target model catches up, it examines these tokens and chooses the ones that make sense, the brown fox, but it corrects the draft model whenever it chooses the token jumped instead of hopped. So whenever we see these two models working together with Speculative, we see significant increases in throughput with them working together. It's a very cool sort of collaboration between these two models. So I encourage you to check it out. NVIDIA actually creates a lot of draft models for Spectec. So these are available on Hugging Face, and you can plug it in to use with GPT OSS. We have one for Llama 4 Maverick. We have one for Llama 3.370B, and a couple other more. So I encourage you to check it out, try running it for yourself. This is an example of what you might see, just significantly higher throughput when you use Spectec as opposed to a base model. Now, another big pattern that we have begun seeing in the past couple of years is disaggregated inference, and this is really taking off across the industry. So we call it disag for short, but essentially what you're doing with traditional serving is you are running both the prefill and the decode stages on the same GPU. And remember, I talked about it earlier. The prefill is whenever you are processing your prompt, building up your KV cache before you actually generate a token. And the decode is whenever you're actually generating those new tokens. And traditional serving, this is all happening on the same GPU. But with disaggregated serving, you are running it across multiple GPUs. So you would have your prefill running on, let's say a single GPU, and then your decode running on a different single GPU. And what we see with this, again, higher throughput, lower latency, sort of combining the power of multiple GPUs to process these prompts and these requests. So there's also lots of flexibility and lots of cool optimizations that come out of this. One of my favorites is the KV cache aware routing mechanism, which essentially your Spectec engine, your Spectec framework will route to the best GPU depending on the KV cache utilization, as well as something called prompt prefix matching. So determining which is the best GPU that already has a KV cache built up that would match best with this incoming prompt. So this is part of NVIDIA Dynamo. Dynamo is NVIDIA's disaggregated serving framework, and it's all open source. Again, I encourage you to check it out. It's very cool. You can run it on AKS. And again, we see significant throughput gains and latency gains with this. So again, I encourage you to follow up and go ahead and explore and try this out for yourself. This QR code takes you to a blog from Microsoft, which instructs you on how to deploy a model from AI Foundry yourself. So definitely test this out. I encourage you to do some benchmarks, test that model out, maybe compare across other models and compare across hardware. Try to get an understanding of different patterns you might be seeing across architectures, sizes, hardware, etc. And yeah, thank you all very much.
Yeah, thanks very much, everybody. Thanks, Stephen, for your time as well. And yeah, we hope you've got some things to take away. And yeah, if you have any other comments, please leave them in the chat.
Thank you, guys. Thank you, Stephen. Thank you, Anthony. We strive to create excellent content for all of you guys, and we would appreciate if you took a moment to scan the QR code that is present on the screen and just shared your thoughts with us about today's session. We appreciate your time and look forward to seeing you here at the Microsoft Reactor. Thanks, everyone.